Hello and welcome to lesson 90 of my DP chemistry curriculum. Today we're going over reactivity 2.3.4. In this section, we discuss how Le Chatelier's principle enables the prediction of the qualitative effects of changes in concentration, temperature, and pressure to a system at equilibrium. We will be able to apply Le Chatelier's principle to predict and explain responses to changes of systems at equilibrium. So, with that said, what the heck is Le Chatelier's principle? Chatelier's principle. As we just discussed in the intro, this is going to help us predict which way an equilibrium will shift in response to any change in a system. What it specifically states is that a system will shift right, meaning to the products, or left, meaning to the reactants, to result in more products or reactants, to reduce the effect of a change. Now, this system only happens, this is very specifically only at equilibrium. If we are not at equilibrium, we're not really talking about Le Chatelier's principle. So how does a system make that shift? Well, it makes it according to three specific changes. Those changes could be concentration, and this is where Le Chatelier's will be most straightforward. It could be pressure, and this is usually as a result of volume. So according to Boyle's law, as we change the volume, the pressure will change as well. Or lastly, temperature. So as we explore the effects of either of these three changes on the system due to Le Chatelier's principle, let's start off with concentration. Now, the most straightforward thing to do is just look at an example. And as our favorite example with equilibrium is the Haber process, we're just going to start off with that. So we'll look at concentration. That will be in moles per decimeter cube inverse first time. And at equilibrium, we know that our concentrations of our reactants and products are constant. So let's make a line for nitrogen. Let's make a line for ammonia, and let's make a line for hydrogen. That will be H2. This will be N2, and that will be NH3. So we're at equilibrium. These concentrations are constant. But at some time, we decide we want to increase the amount of N2. So we pump some more nitrogen into the chamber. Now, Le Chatelier says it wants to resist that change. So it wants to decrease the amount of nitrogen in the chamber to resist or balance that change. So the reaction will start moving the reaction will start moving forwards, consuming nitrogen. If we look at Le Chatelier's H2 plus N2, will react to form NH3. So if we add more nitrogen and then we shift the equation forward, we'll reduce the nitrogen. So we may end with more nitrogen than we started in the chamber, but Le Chatelier's will try and minimize that difference. Now, if the reaction is shifting forward, we are going to be increasing the amount of ammonia. And so we may have more final ammonia in our chamber. Furthermore, because the reaction is progressing forward, we will decrease the amount of H2 we have and thus end with less H2 than we started. So by introducing a reactant, by introducing Introducing a reactant, the reaction shifts right to consume it, thus minimizing change. So that is Le Chatelier's principle in a nutshell. And by shifting to the right, we are shifting towards our products, making more products overall. We can simplify this by saying both adding reactants as well as reducing products both of those will create a shift towards products, which is, of course, a shift right. By, by adding products and reducing reactants, that will be a shift towards reactants. And that's basically Le Chatelier's principle in a nutshell, specifically when dealing with concentration. But we can start applying this forward as we now move on to both pressure and temperature changes. So let's look at pressure. Pressure only affects systems with gases. Only affects systems with gases. And the reason that is because we know that solids and liquids are not compressible and therefore are not affected by pressure, or not so much. Furthermore, as we mentioned before, this is due to changes in volume. So this is pressure is changed due to volume. And remembering Boyle's law, an increase in volume equals a decrease in pressure, and a decrease in volume equals an increase in pressure. Kind of like if you squeeze a balloon, you're adding pressure and you're decreasing the volume. Those are inversely related things. Now, how do we actually determine the shift? So to determine shift, we must first count moles. Moles of gas in each side of reaction. So for once, I'm not going to use the Haber process, but we'll come back to it later. Don't worry. In this example, we'll say 2 sulfur dioxides, gas, plus 1 oxygen, gas, is in equilibrium to produce 2 sulfur trioxide gases. We have 2 plus 1 for 3 moles, and we have 2 moles. To figure out the moles of gas, I'm just looking at coefficients. So 3 moles of gas on our reactants, 2 moles on our products. And then we can start saying that to change or resist the change of pressure, we can see that an increase in pressure, so the system is feeling more pressure and it wants to reduce that, it will shift to fewer moles. Because if we increase the pressure, converting 3 moles to 2 moles decreases the amount of gas in the chamber, and therefore the pressure will be relieved somewhat. So to resist, we're going to shift to the fewer moles when we have an increase in pressure. Conversely, a decrease in pressure that will shift to more moles. Now, it's kind of hard to figure out why this really is, but when we increase the pressure, we're actually changing the number of collisions. As we learned in collision theory, a higher pressure, usually caused by a lower volume, means more collisions. And we're going to have a lot more collisions where we have more moles than less more moles. So until it evens out, our larger number of moles will move and react faster than our smaller number of moles, thus shifting our equilibrium to the fewer mole size. Now, again, this only works with gases. And furthermore, this change only works if there are different number of moles of gases on either side. So if we have 2 moles and 2 moles, there's no fewer side, and therefore a change in pressure does not have any appreciable effect on our system. All right, moving on to the last possible way to change system, which is temperature. Now, for temperature, we first need the overall enthalpy value, or enthalpy change of a reaction, because enthalpy tells us how heat is exchanged in and out of a system. So I said we're going to come back to it. So let's look back at the Haber process. We have 3H2 plus N2 reacts to form NH3, 2 of those. And that comes with a delta H of negative 92 kilojoules mole inverse. So we notice here that this is a negative value. And when this is a negative value, we know that it is exothermic, meaning heat is coming out. We are producing heat. Heat is a product. So in exothermic reactions, we are making heat, while in endothermic reactions, we are consuming it. So heat is a product. So knowing that, I'm actually going to rewrite this equation. I'm going to say 3H2 plus N2 reacts to form 2NH3 plus heat, because now it is its own product. And now that it is one of its own products, we can apply the same rules we did with concentration. If we add heat, we'll shift that way. If we reduce heat, we'll shift to the right. So this becomes pretty self-explanatory because we can just apply the same principles that we learned for concentration. And we can say add heat, shifts right, reduce heat, shifts left. So this is the way that we get to, oh, you know what? Sorry, I just realized I made a mistake. I meant right and left instead of left and right. Sorry, got those mixed up. If we add our heat, we're going to shift over to our reactants. If we reduce our heat, we're going to shift over to our products. All right, so those are how these can affect our equilibrium. Now, out of all of these, only one thing can affect Kc, and that is temperature. When we shift our equilibrium in concentration, when we shift our equilibrium in pressure, we still end up getting an equation where the Kc will stabilize at the same value. However, when we shift our equation by temperature, we are not actively adding or reducing any concentrations. Those are happening naturally through the addition or removal of heat, which means our equation Kc will shift. So we just saw that in an exothermic reaction, adding heat shifts towards reactants. So if our reactants are increasing, therefore Kc decreases. Because remember, Kc is effectively the concentration of products over the concentration of reactants. So by increasing our reactants, decreasing our products, our Kc value will decrease. Furthermore, removing heat we will shift towards products. Therefore, Kc increases. And if this is how it is for an exothermic reaction, endothermic is inversed, as heat is now a reactant. So I'm just going to cut to it. Kc increases with heat addition. Kc decreases with heat removal. So that is how our equilibrium constant changes with temperature. The final piece of this entire lesson is actually talking about catalysts. So Kc and catalysts. Now we remember that a catalyst increases rate by reducing activation energy, by providing an alternate route. If we look at it graphically, which we've done a few times, and then we add our catalyst, you'll notice that the activation energy is reduced by the same for both the forward and reverse process. Therefore, rate of forward and reverse reactions change equally. If that change is equal, then it therefore has no effect on equilibrium. So catalysts have no effect on equilibrium. All right. So there was quite a bit of things that we went over in this section, but the main points are how Le Chatelier's principle will help us understand that a system will reduce or try and minimize any changes made to it through pressure, through temperature, or through concentration, as well as the equilibrium constant Kc is affected by temperature, and lastly, that catalysts have no effect on equilibrium. I hope this helps and have a great day.